All right, we're going to begin our study of reducible and irreducible polynomials with Gauss's lemma. But slightly before that, we're going to consider why this is kind of a hard question. So consider the following polynomial: t to the 16th plus t to the 15th plus t to the 14th, all the way down to plus t plus 1. Okay, so you just decrease the exponent by 1, add it in. The question is this irreducible or is it reducible? Well, how might you go about checking this? Well, the first thing we might do is we might rule out linear factors. Because if this factors as a product of two polynomials, one of the polynomials could have degree 1. This is the same as roots. Now, a quick test with the rational root test shows that I should clarify this means over Q. A quick rational root test application will show that it has no roots. Fine. Okay, so it has no linear factors. But so this would say cannot factor as degree 1 times degree 15. But it could factor as degree 2 times degree 14. So then you'd have to rule out quadratic factors. So what would you do? Let's call this polynomial f. You would say f is a quadratic term. We can assume it's monic, so the leading coefficient is 1 because our starting polynomial is monic. And then a degree 14 polynomial. And we'd have to show there's no possible way of arranging the coefficients. I'm not going to write the coefficients for the degree 14 one, so that we get something that works. This is automatic. This is already difficult, right? The linear factors is almost always easy. But just because you don't have linear factors, it doesn't mean that you don't factor, okay? So this is now very difficult. And then what do we need to do after we do that? Either we can find a factoring or we can't. If we can't, we would then need to rule out cubic factors. And we have to keep going for all possible ways of having two polynomials have their degrees summed to 16. So this is like 1 and 15, this is 2 and 14, this is 3 and 13, and so on, and then we'd have to go all the way down to 7 and 7. This is a nightmare. I hope we can all agree that this is not something that we want to do. Yikes. So let's put some storminess about it. Nightmare. Now we're going to find out later, as a consequence of some of the results, that this polynomial is in fact irreducible, and polynomials like it will be able to detect if they're irreducible quite easily. Okay, so roughly it has to do with the power plus 1 being prime. So 16 plus 1 is 17, which is prime. All right, so our first steps, I should say, is a lemma called Gauss's lemma. And what Gauss's lemma says is that if you want to check irreducibility over Q, it suffices to check irreducibility over Z. So let f be a polynomial over Z that is irreducible over Z. Then f is also irreducible over Q. And this seems kind of like whatever at first, but remember, here over Z, polynomials can factor kind of in less ways. And this says by adding in the ability to have fractions, we still cannot factor further. Okay, so irreducibility over Z implies irreducibility over Q. Now, let me show you one way in which this is helpful. So as an example, t cubed minus 5t plus 1 is irreducible over Q. And the reason is by Gauss's lemma, which we're going to prove, it suffices to show irreducible over Z. And so what can we do? Well, we can try to factor it over Z. So t plus a, and then t squared plus bt plus c. Now, t plus a being a factor, all that says is this guy can't have, if it's a factor, then we'd have an integer solution to this. And one can sit here and one can show that there's no integral root of this polynomial. In fact, by the rational root test, it should be plus or minus 1. But let's forget about that for a second, and let's see how we might do it a different way, in a way that will generalize to maybe if this was t to the fourth minus 5t plus 1. So we don't necessarily are looking at a linear factor. So if we were to multiply this out, our quadratic term would be a plus bt squared. Our linear term would be c plus abt. And then our constant term is ac. Well, by comparing coefficients, a plus b had better be 0. C plus AB had better be negative 5, and AC is 1. All right, so what this is saying is A is equal to negative B, C plus AB is negative 5, and A equals C equals 1 or negative 1. Because we're over Z, right? We just need to check over Z. We don't have to consider cases where A is like 2 and C is a half. A and C have to be integers, and the only way two integers multiply to be 1 is if they're both 1 or they're both negative 1. Okay, we may not need this bottom case right here right now, but we can see already that reducing to Z makes some simplifications. Let's go ahead and plug in equation 1 into equation 2. Then we get A is negative B, and if we plug that A is negative B in, we get like C minus B squared is negative 5. All right, so this is saying A, and then of course A equals C equals 1 or negative 1. This is saying A is negative B and C is B squared minus 5. And then A equals C equals 1 or negative 1. And so C has to be B squared minus 5. Maybe I want to write this as differently as C plus 5 is B squared. And A equals C equals 1 or negative 1. So if C equals 1, B squared equals 6 is impossible because we're over Z. If C equals negative 1, we get B squared is 4, which would tell us B is plus or minus 2. If B is plus 2, then, well, actually, in either case, if B is plus or minus 2, then A is negative B, so A is minus plus 2. But A has to be 1 or A has to be negative 1 in this case, and this is a contradiction. This is way more complicated than we need for this problem, but it illustrates that instead of working over Q, working over Z, we can make some simplifications when we check irreducibility. So this is the utility of Gauss's lemma, and you'll have opportunities in class to practice these kinds of arguments. They're very important arguments, so you will be able to practice them. All right, let's prove Gauss's lemma now. So again, what Gauss's lemma says is that if we're irreducible over Z, then we're also irreducible if we allow for more numbers over Q. Okay, but only fractions, of course. We're not adding in like square roots or anything like that. We're just adding fractions. All right, so proof, of Gauss's lemma. All right, suppose, F is irreducible over Z, but for a contradiction, F is equal to G times H over Q. Meaning G and H maybe have rational coefficients, honest rational numbers, where like it's like 3/2 or something, where it's not actually an integer. All right, so suppose that it's reducible over Q, but it's irreducible over Z. Let's let N be the product of the denominators in G of the coefficients in G and H. Okay, so I list out all the denominators. I compute their product. That's again an integer. And I'm going to call the integer n. It's a non-zero integer. Then NF is NGH. And we can clear, right, some of n is the product of the denominators in G, and some of it, the rest of it's the product of the denominators in H. We can use n to clear the denominators. So it's G prime, H prime. Here, since we've cleared the denominators, G prime and H prime are over Z. Okay. So what we're going to do is, we haven't arrived at a contradiction yet, of course, because just because F is irreducible over Z, it doesn't mean that NF is necessarily irreducible. So what we need to do is we need to cancel the n. So we multiplied by the n, now we need to divide by the n. It would be silly to do that though, and it would just get G8. So what we're going to do is we're going to divide by the n carefully. So what are we going to do? We will cancel every prime factor of n on both sides while remaining in Z of t, in the polynomial ring over T. Let me scroll down a little bit. All right, so that's the strategy. We're going to go and we're going to show you how to cancel every prime factor of n, and we're going to do so in a way that remains with integral coefficients, okay? And that's going to be where our contradiction is going to show up. So what can we do? Well, we can write G prime as some G0 plus G1t plus GR t to the r, and H prime as some H0 plus H1t plus HS t to the s, where, of course, our G's are integers and our H's are integers, because that's how we set this up. If P divides GI for all I, then we can replace G prime. Sorry, let me back up 1 second. Let P be a prime factor of n, be a prime factor of n. Okay, if n has no prime factors, n is 1 and we're done. Otherwise, it has prime factors. Take one of them. If P divides all the coefficients in G, then G prime over P is, of course, still in Z adjoint T, and we can replace G prime with G prime over P. And we've gotten rid of one of the prime factors. Similarly, if it divides all the coefficients of H prime, we do the same thing. All right. So what can happen? Well, it must be that if P doesn't divide all the coefficients in G and P doesn't divide all the coefficients in H, there exists a first coefficient in G and a first coefficient in H. So there exists smallest I and J such that P does not divide GI and P does not divide HJ. Okay. So there's a smallest such one where this is true. Because if it again divides all of them, then we can replace the corresponding polynomial with that over P. All right. But notice that P, of course, divides NF. So P divides G prime times H prime. and in particular divides all the coefficients of G prime H prime times H prime. That is, it divides I and j. It divides the t to the I plus j coefficient. This coefficient is h0 gi plus j. Remember, it's all products. It's the sum of all products of coefficients where the indices add up to I plus j. So h1 gi plus j minus 1. And then we're going to hit hj gi, and then we're going to go of course, all the way down to this guy. All right. So I know that p divides this coefficient. So p divides this guy. But we also know that p divides all of the coefficients less than hj. So p divides this one, p divides this one, and p divides the one right before this. Also, going from right to left, p divides all of the coefficients of g that are less than I. Well, p divides this one, p divides the next one, and p divides all the ones up until you hit I. Now, it could be that, I is 0, in which case I wouldn't write any of that, of course. So p divides the whole thing, and p divides every term except for the middle one. What does that tell us then? Well, p must divide the middle guy. But p is prime, and Euclid's lemma from number theory tells us p must divide one of them. And this is our contradiction. It's a contradiction, of course, because we assumed that it doesn't divide either of them. All right. Okay, so what must be true? Well, it can't be that if we have a prime factor of n, that it can't be that it doesn't divide all of the coefficients of one of them. So it must be that p must divide all of the coefficients of g prime or all the coefficients of h prime. And I'm just going to write it like this. Replace accordingly, as we said before. All right, so we replace this accordingly, and we've canceled a prime in n, and we do it again, and then repeat. Okay, and each time you do this, you stay within z, and eventually, there's only finitely many prime factors of n, you just keep canceling them. Eventually, you have a factorization inside of z. I guess, let me not end the proof there just yet. Then we can write, after we've canceled all the prime factors of n, there's just there's just a 1 left, and we have some g double prime, h double prime is a factoring in z adjoint t. And of course, the degrees never change in this process. This is an honest factoring of terms of smaller degree. And this contradicts the irreducibility of f over z. Sorry, this video was a little bit longer than I wanted it to be. I guess I've said that a lot. Of f over z. And that completes the proof.